Okay. Yes, I gave you an assignment on how to summarize what you learned so far. So far, you've been working with within this numerical modeling. You have been introduced to model building here, and the software. In this case, it's Mathematica we are using, and a little Excel. Lots of significance, matrix inversion, linear and polynomial interpolation, smoothing, data curve fitting, some statistics, and data linearization, multilinear regression. And today, this refresher, I'll try to give you a practical example based on some data I collected during my master 17 years ago. I think that one is quite good because you come around a lot of these topics I just mentioned. You can see there is a link here, and that's because the inspiration to solving this, I found it quite hard to find some material at the net which could support me in how to solve it in Mathematica. I'm used to SAS and MATLAB, but Mathematica is a little new to me, so I had to Google a lot, and this site here has some really nice lectures within the domain. Let's have a look. Of quantitative analysis in life science, and I'm from life science, and I am an agronomist. But what was interesting for me was this part, general linear model. That was the one interesting for me, and you can download this guide here if you want to play with it yourself and be inspired. But let's get back to what it's all about today. I'll come around, it's about nitrous oxide, flux, N2O, and the factors affecting the emission in Giganteus, Giganteus, and winterized soil. In fact, it's not winterized, but it's Statistical, and that's a hybrid between rye and winter wheat, but that's not so important here. But let's see. Just to summarize, so in the autumn of '94, I had this trial where you have Giganteus here, which is a monocot C4 plant which can grow really fast, also in Denmark when it's hot. And then here we had Statistical. It's a quite sandy soil, and these one were used to collect the flux of nitrous oxide in short periods in the morning and the evening. But what we did here was that we took some soil samples from the Giganteus soil and some soil samples from here. And then we put it into, I don't know if I can, let's see. This one is awake. 1 second. Blue. So we had some soil from here. We put it into a bottle. So there's some soil here. We added some water, and then we blocked it, and we kind of mixed it all the time. And at a certain period there will come N2O up in the airspace here. We collected the samples, analyzed it in some small tubes, and we did that for this field and this field. And what we mixed into this one to see the effects, what can really have an effect is nitrate and carbon in form of glucose. And then this is a part of denitrification, so the next step from N2O, to make it short, is that it can go further to pure nitrogen, and that's not nice to have in the atmosphere. But this one is bad. It's 320 times stronger greenhouse gas than carbon dioxide is. So that is really a bad one. So what we want to look at is what is the effect, is a tendency for higher production here compared to in this soil which is plowed every year. This one is perennial, so it's there for several years. Yeah, that was a short introduction. Let's see how I get rid of this, like that. So, and then we collect the samples, and I end up again with this thing. So we collected samples. So if this is time, and it was stating here it was for 6.5 hours, then we have N2O here. So we collected samples like this. That's the accumulation in the space of this bottle. As you recall, you had the soil here, and then up here you will have the N2O. So that's an accumulation, and what we want to see is this one different from, if I can, from, for example, another one which will be here. Is there any difference? So that's the whole core thing. I have that in a big Excel file, but I want to get it into Mathematica. I can try to find it for you. So here is the Excel file. So you can see the stored, what is the name of the crop, is added acetylene. And there's a sub-trial number, and that's because you could not run all of the bottles at the same time. You have the glycosis, you have nitrate, and you have the time in minutes. And then you have the accumulation in nanogram, nitrous oxide, nitrogen per gram dry soil. So if we scroll down here, you can see how it evolves. It's just increase the number. So there's 16 different numbers, and then you repeat it again. So if at different treatments you are running at one time, I think it's approximately 4 or 8 bottles you're running. So this is what we have, and we want to get that into Mathematica. So let's have a look at that. It takes time to go through this, but I think it quite well show how you work when you want to analyze some data from the field. It's a complex thing, but Mathematica is a nice tool to do it with. But there is quite some things you need to learn before you can really handle it. But the thing here is that you use import. And then we first set the directory up here. I get that into a color which is nicer. First we set a directory, and that's the notebook directory. So that's where this file here has been opened. That's also where this Excel file will be. So then you don't have to set the path. If you wanted to set the path, you can just say insert and file path here. You point that one, and then you can add it. That's not so nice way to do it, but it's fast. Then we want to look at the header. That was the first row. If you recall Excel file, we want to get it into data. And this one is saying that you have a big chunk of data. And here you can see the sublist saying that's the headers from the Excel file. And then you have the first data and the new little sublist. And that's it. Here we take the header file, you can see up here, and it looks like this. And when I flatten it, I only take from the second row, and this means all of them. I say row because I'm a MATLAB guy. Then I end up with this setting. And the reason I flatten it with this is because I ended up with 3 curly brackets here, and I only need, you can see here, I only need 2 in order for, so kind of I reduce a dimension I don't need. So that's what I do with flatten here. If you're in doubt with all these commands I'm using, you have to pause me and then use help. I hope I can upload this file, this NB file, to TeacherTube, and then you can find it. I think it's in the text following this YouTube. So if you want to inspect the data, we just have a look at the dimension. It's saying there's 2,177 rows. That's exclusive the header, and there's 7 columns. So if I say I want to see it, I thought I removed the header, but apparently it's not removed here. If I want to see the data, or you want to do it, you can just try to remove this, and you will get a huge chunk of data. The reason here, you can see I get the data header, the trial data. It's kind of double config, but it's because it's been made over a long period. But what you end with, and that's important, is that you have some nominal factor or factor variables, treatment variables, I don't know, the nominal variables is probably the right, but it's hard for me to pronounce it. And what you have there is the crop. It can either be, let's have a look at that. We have something with acetylene, we have a subtrial number, glucose, and nitrate, and it would be nice to know what values it can take, but we will let Mathematica do that in a second. Then you have a covariate, and that's the time. You remember you had this time in this direction, and you had the accumulation here. So that's a covariate, and then you have the dependent variable or response variable, which is the rate of nitrous oxide. So let's have a look. So what we do here is I just take the headers, so I know the headers. I have them here. I did that before too. Then I use gather, and you have to look to help, but first we have to start from inside. First I sort the data according to all, and they say here range 5. So I sort according to range 5. So first according to crop, then acetylene, then subtrial number and all that, and after that I say gather by and what that means is that I collect, one second, so I'm back. I rearranged it a little so it's easier to look at. So what I do is you take a table, you need to get the factor, the possible values in this one. So I use table, and table I have A, which can run from 1 to 5. So that's columns, and if you look at what we had, where it's listed, 1, 2, 3, 4, 5 columns. So that means that I sort according to that. So I sort first according to crop, and I only take that column. So it's only crop I have in this output. And then I gather by, it means that I collect possible situations. So with crop I have Giganteus and Cecale. With acetylene I will have 1, 0 and 1. With subtrial numbers I will have up till 16 and so on. And then I use table form here to make it look nicer, so I can have crop. I can see it here, it's listed, so it's an easier way to look at it. So this is what I do just to see what is in the data. So here's an example of how we get the data from a specific row. So we say, if we call that filtered data, so we say we need to use select, press F1 if you want more. We use data, that was all the data except for the header, if you look in the Excel file. So all data here except for the Excel file. So what this one is saying is select from data from, use pure functions here, column 1, that's crop, but it needs to be equal to Sikale, and column 2 needs to be, so that's Astulane, no Astulane. And the reason I use this is because there's an arrow when you imported it, or arrow on arrow, but that's how it was in Excel. This is imported as chars or strings. These here, you can see there's no dot behind it. You need to take care of that, or be careful when you import from Excel. The rest here have a dot, so that means that it's a numerical value. So the next one, which is column 4, you say that it's equal to 0 here, because now it's a numerical value. And then I say that I want all what's it called, rows, if you look at it as a matrix, but I only want the output from 3, 6 and 7. And 3, what was that? That was subtrial number. It's because I only extract these things, so I only need that. The time and the flow, or the production. So now I extracted that. So now let's illustrate it. So here what I do here is I sort the filtered data according to the first number in the list, or I will say the first column. And the first column here was subtrial number. So it's gather them in sublist. And what you then do is, it's just to identify the subtrial number, I forgot that. I drop everything except the first one. So that means when I have a list with all these measuring points, you have to play with it to learn to know it. But then I know there's a subtrial number 9, 10, 11 and 12. So let's try to fit a linear model which depend on the numerical subtrial numbers. Fit a second order polynomial based on d time, and let's take the double interaction. The way you do that is you just say we have the filtered data, so it's just on the limited data now. I say that I have a model containing filtered data, and the variables I have is subtrial, that's the number of the bottle, and I have d time. And then I say I have subtrial, d time, and I say the nominal value variables is the subtrial. So that's the number of, that's the bottle, so to say. And I take the second order polynomial and I have interactions here. Then I get this model. And you can see if I just look at that, whoa, it's really, everything is important. I'll come back to why that's the case. This is just an introduction to how to get the data on the limited. And then we go into action. The first thing is that you do the same here. You find the groups by using this gather by and drop. If you want to see it, you use show, And then list plot, you take the groups. That's what I got here. And then you plot all the data. So you can see it here. What you plot is in the second order polynomial. You had this model. I'm a little confused, 2 seconds. I'm back again. So what you do here is that you sort the filtered data. Remember that was trial number, the time, and the response, the accumulated nitrous oxide. What you do here is you sort according to, or then you gather according to the first column. That was the sub-trial number, the bottle number. And what you then do is you say drop. I want to drop something. I don't want to drop anything here, but when we go into the list, this means that you want to drop the first column. And the first column was, if you recall that, because now it's sorted into sublist, where there's a sublist for each bottle. You want to drop the first column, and that was the sub-trial number. Because when you do that, then when you go into list plot here, and you say groups, then it will plot, it will only have the data. So that's a quite nice way to get all these points. And then here, what you do is in order to get the tooltip, you have to go all the way in. What you have here is linear model fit. That was the one we made up here. And then what you want to do is, you want to do that for each of the output. There were several, I think there was 4. Where are we? Back again. It's not easy to remember such a big file. But what you do is that you have 4 of these fits fitted second order polynomial, as you see here. So you take each of them, and then it inserts t from 0 to 355 minutes. And when you put tooltip around that, that means that when I do like this, I can see the bottle number. So it's a nice little function. That's the filtered sub-trials it's using to do that. And of course, you set the image size here. But that's it. So now you seen how to, let's collapse that one. And this one, I think. So now we're into action in analyzing the real data. So now the first task was to import the Excel file named this. So that's what is done here, and you prepare the data as you see. So now hopefully I can go a little faster. And yeah, the style, if you haven't seen that one, I just put in some text which I can color. So if you look at style, I just have here italic, bold, blue, so it's easy to recognize. Gather in subplots, list according to crop, acetylene, sub-trial number, glucose, and nitrate. So that's also what you can see here. You can see you have here 1, and it's just continue, and that's several of them. And I say there is, if you look at these, there's 64 of them, different combination. And within them there's 34, and then 7. 7 is, as you recall, all these, and then you have d time, and you have the response. So that was the first one. I think this is a leftover. 2 seconds. I'm back again. What was missing was this little star and bracket. So the comment was disturbing this one. So now here you can see all the plots just as lines. Get an idea of how much there is. So here we want to create the full model that's asked for having everything. So what we do here is that we just try to calculate the full model. So that's what you do here. You take a linear model fit, take the trial data, and then you use subsets. It takes all the combinations of these in the first and the second. So it takes a combination 2 and 2 and put that in here. And you say that the model depends on crop, acetylene, subtrial number, glucose, and nitrate, everything. And the nominal values it is. And then you end up with this super huge model. I printed it just so you can see it. That's really a lot here. I'm not going to detail that. I will go into detail how to read it later. But you can see how subset works. That means that it takes all combination. If I apply times, it will just do like it's multiplying these two. So you can see here that first it takes the first ones, the ones with the lone main factor, then it takes the combination 2 and 2, and that's what happened above. So let's have a look at the model. If you can see here, it has all the main factors, and then it has the two-way interaction. So that's the interaction between acetylene and crop. And you see everything is really significant here, highly significant. Remember, it needs to be smaller than 0.05. That's 5%, or even better than smaller than 1%. So this is super high. And here you just ask parameter table for all the different parameters. It's just to show that everything is important here. So what is wrong? There's something wrong. The problem is that the data is not independent. The problem is when, I don't know if I can do that with a drawing. If I can get. When you have your bottle here with your soil and the water, then you take samples again and again from here and get the points. So of course when you have this point, you will expect that this one will be closer related to this one compared to this. And if you have a new sample, this is another bottle, it looks like this. So these points are really related to each other. If there's high speed here, it will probably also be high speed here. So it's violating the assumptions, which is one of the most important in the model, that there's independence between the samples. So how do we get rid of that? The way to get rid of it is to use a fit function. So if you recall that we had the second order, it looks like a second order, the point. So if we fit, for example, this would be nice at D grade, but the problem is we cannot really we cannot really get that out of the data. If we go back, where do we have it? Yeah. Here it looks like this. So here it was. Let's see, where am I here? So what we need to do is we need to fit some kind of model, and then if we get the derivative, if we had this one, we could find the maximum of it, but we are not there. So if we can just get, let's go back. You can just get the slope, then compare the slope, for example, out here. That would be really nice. So let's go for that, because this model is useless. So what we do here is that we kind of repeat here, but now we try to get rid of the dependent variables. But let's first have a visual inspection, and that is really important. You need to look at the data first. So we use the gather by, first by these columns, and then the third one is the subtrial numbers. So we gather by that one as the last one. And style here is just kind of make up on what you look at. So if we look at the data here, this is what is then in the data, which is collected together. So you see all these are the same. And I made a little jump just so it's easier to look at it. But you can see how it changed. So all this data is now arranged, so I can start looking at it. So I do that by using table. Style is not to make the plot, but that's to make this. So with using style, I'm saying within that table you need to write this, change line, this backslash n means new line, so it jumps down here. Then I want the output here from the first one. What is B? That's these 16 different subtrial numbers. I know from earlier there was. So it will take that and plot it so I can see which treatment is. So this treatment is, there's added acetylene is Giganteus, and have not been added glucose or nitrogen. Then I put grid line and an orange one here to indicate there's something wrong, which we will come to now. So if you look at this data, you can see there is an accumulation, and if you add, for example here, that is glucose, you can see there is a tendency to its higher speed, but something is wrong with some of them here. So we need to overcome that somehow before we start to fit a function. I think a second order polynomial will be fine here showing this. And this function will probably also, but because I don't like what is happening up here, it will give me wrong conclusions. I'm cutting off here at 200, so I say I only want this, and there I find fit a second order polynomial. And surely I think second order polynomial can do this fine. So that's what I do here. I use select, as you've seen before. I take the trial data and I say, okay, look at it in all subsets in the data, and look in column number 6. And if that one is smaller than 200, then include it, and I get this new data set. Then I sort it according to row 1, 2, 4, 5, and not the last one. I'm using the subtrial number as the last one to sort after. And I have 16 different subtrial numbers. And then just to have fun here, I don't know if it's important, but it was nice to have some headers to look at. the data, so that it's a different combination. I don't know if it's smart, but it was a fun function. So what you say, you use apply, that means that you have a certain function, that's times, multiply, you have what means a rule, that's this one, multiply it, and there's no space, it's kind of this one is multiplied with this one. And then you use union, is just finding what is special in these combinations. So you have all the different combinations here. And then you just get rid of curly brackets, transpose it, and put it on this one. And you do that for all 16 subplots. And you end up with this. I don't know if you can use that. It's we are trying to automate it, a PhD student and me. But if you want to approximate a second degree polynomial and compute the derivatives at times 200, that was where we're cutting, so that was at the end. What we do there, a lot is happening here. We use the table function. It's a neat little thing that what is happening here. But if you just look at, we have the linear model fit, we use the two last columns, that's 6 and 7, so that's d time and the accumulated amount of nitrous oxide. And we say the model is a second order polynomial, and we have x with this time. Could have used t, but what we then do, if you remember this, we have to go in, okay, it used b here. So that's all the data. But b is using a. What is a? A is temp4. So temp4 is all these small subplots or sublist. So within this sublist there is 4 bottles. So it will take these 4 sublists for a subtrial number with d time and everything, put it in here. So this one will take these 4 sublists and we'll use one of them at the time and fit a model. And when it has done that for the first 4 bottles, it will go on to the next one. So you end up with all this, because what you do when you have all these models, then you see this here will be put on here. So it is saying I want to differentiate this model where x is 200. So then I get the estimated speed at the kind of, can I roll back so far? I get the estimated speed here of the second order polynomial for all of these. So that's what we have here. So if I mix this funny thing I had up here with the output of the derivatives, I get this. So for added acetylene, the crop is Giganteus, and you have glucoses, not added, and subtrial number 1. You have 4 different bottles. So this is the speeds. We can also look at it in another way. Here I just make a new data set saying that I have table, I have append, so I just take the data from A, and A is 1 to 5, derivatives from 1 to 5, 2 to 5, that's because this is number 1. And I append that on what I get from the first one, that's crop, acetylene, and glucose and nitrogen. So that's what I have here. And then it's arranged it like this. So now it's easier to look at. But it's not really a nice way to calculate on, because if I want to calculate, I would like to have one column here and the different treatments. So you have to pause and use help if you really want to figure out what's happening here, because it will take too much time to explain all of it. So what we do here is we use append again, and we use table. So we run from 1 to 16. we take the derivatives, and then we take here from 1 to 4, we take the first 4 of these, we just steal them and put them on, and then we get this. So we can look at the derivatives now and start to work with them. I have a cat, I don't know what's wrong with that one. They get active when it's late. Cannot show it, I don't have a web camera, but now we have the data, so now we can make the true model, where now we are rid of the dependence between the points, because now we only have a slope for each subtrial number, or you can say bottle. So here we make the linear fit, saying that we have a different 2 seconds, I have a cat to. Where were we? Now the cat is out, at least one of them. We had the function here with all the different two-way combinations. Look at subsets. We use time to generate it. I don't even think that is necessary. And then we have nominal variables here, which is crop, acetylene, glucose, and nitrogen. So here we get the result. And you see the numbers here is a lot smaller than before. And now we have the two-way interactions. Some of them are not of significance. You can see this one is not important. This one is not important. And this one. So we should remove them from the model to get a simpler model. So let's do that. And we end with this model when we reduce it. Yeah, I just wrote them manually, the one I want. So now we can see everything is significant. The effect of glucose and nitrate, adding that at the same time, is important, but it's on 5% level. It's not at the 1% level. So it's not that clear. So now we can start to look at the model, the parameters. So you can see there is a clear effect of the crop p-value. So it seems like if you look at it, Giganteus, when you have Giganteus, you really have a high nitrogen or nitrous oxide production or rate compared to if it was not that was Secale, then this one will be 0. And acetylene, if you add acetylene, then you have to inverse this, then there will be effect. It will add the speed will increase. And the same glucose, if you add glucose, the speed will increase. The same here. I'll show you how to calculate it later as an example. And the interaction means that if you add either acetylene or glucose, then, or both, then it will have a negative effect. So it will damp the effect of the main effects. So it starts to get complicated to read it when you have interaction. That's also why we only use two-way interaction. Hard to handle the rest. So what we're doing here is try to show the true model, how it looks. So, and how you put it into the model. So this is how the model looks. It's saying that you can recognize the numbers, I think. Can we see both? No. Okay. 1.03 you have here. So that's the numbers. You can recognize them if you Now we can. Why don't I do that? Wrong one. Come on. So do like this. Pause. Now I'm back again. So I managed to collapse the right amount. So now you can look at the model. So I thought I was doing this. Help. Okay, I give up collapse it, but the way you read it is that you need to take this number, subtract this, and then discrete indicator means that if acetylene is 0, it can either be 0 or 1 is stating here. Then if it's 0, it's true, so you multiply this number with 1. If it's not true, for example, if this one is 1, you multiply it with 0, so this disappears. And this is the way it works for all of them. So that means if you add this to the model, that's how you put it in the true model. You write Giganteus, and 1, the way you do this, remember this was a string, and this was numerical value, so this is acetylene. If there's acetylene, added glucoses and nitrogen, then you will get this value. This is what I do here, if you want to see how it's done. You can see the true model reduce Giganteus 1, 1 and 1, and then this will end out as the output you see here. So this means that this will be the production or the speed, production speed or accumulation speed of nitrous oxide. So the next question was, what is the effect of adding acetylene, nitrate and glucoses to soil? And that gets a little complicated, but if we just put it here, all of it, this is all the combination. I generate, let's see, the table here. So this one is generating because first I take acetylene, so I rearrange it all, then I take the crop, glucoses and nitrogen. So this table is the first part of this. Then style is just the words I'm putting here. Then I say I want to append these treatment combinations, you've seen it before, with the true model, and then I add with pure function the treatment combinations. I use apply there. So it'll insert this to the true reduced model, and then the output will be put here. That's the output of the model with the different settings as you saw before. So now I have all the different effects according to the model. I could also start to look at the residual plots, but probably advisable, but I haven't done it to see if the model fits well. Or probably it is advisable. Then if I want to present this, I can rearrange it like this, or I can scale it. So this one, I take this one and say that is 100. So this will be 0.99 divided with this number multiplied with 100. So then I get these numbers. So now they're scaled, so they're easier to look at. And what I do here is, because when I add acetylene, that's the same as saying, how should I say, when you have these denitrification in the soil, you can either have screen draw. So if you have this pool of soil and water, in there you can either have it as N2O, or I can take one more step and it can end as it's late pure nitrogen. But you can cut this by adding acetylene. Then you cut this, so everything is accumulated as nitrous oxide. So that is what I say, what is the ratio here between with and without nitrogen? Where do we are? Well, here, fraction. Treatment effects, I take the first two and divide it with the next three, because the first one up here, these up here, was acetylene, or not added acetylene, and this one was where acetylene was added. So if I divide that one with this one, I get 0.78. So that means that 80% of the production of the denitrification is in fact the nitrous oxide. Yes. I almost used an hour, if you're still awake. Here I try to show how the model works. So the model looks like this. You can go back in the presentation about 5 minutes. So yeah, here I can see it. Here you have the different parameters. This was what I was looking for before. So what you have here is, these are in fact the important ones. So it's kind of the same which happened here. So what I say, if I want to calculate this manually, and I want to calculate it when the crop is Statistical and nitrate has been, I forgot this, added. What I do then is, we start with this value, then plus, then we take this value and we ask, is this Giganteus? Yes or no? No, it's not, it's Statistical, you can see that here, Statistical. Okay, it's Statistical. So we multiply with 0, and so on. Has acetylene been added? I forgot to state that here, but it has not been added in this case, because it's saying acetylene is 0. If that one is 0, multiply with 1, and so on, and then we add it, and we get this number. And where does that number hide? I kind of jumped to, so you can see that this number here, that was where Statistical and nitrate, and then I forgot acetylene. But we have Statistical here, we have glucose and nitrate, so we have to find, that's this column here, and acetylene is this too, so it's this one, 0.31. That's in fact the same we get here. The way we calculate this is, I'll come back to that, or how we get Mathematica to do it. So the two-way interactions is perhaps a little hard to comprehend. You have to look at it for quite a while and wonder how is this calculated. But it means that if you look at this interaction, it kind of, you can read this text. I tried to formulate it there. But it means that if there's either Giganteus or nitrate added, then you have to subtract this. So it means in all other cases where it's either nitrate has been added or it's not miscanthus, it has a positive effect. So it will be added to it. I just need to verify that's what I stated down in the text. 2 seconds. I think it fits with what I said. So it's kind of course, when you have miscanthus, you have this huge effect. But when you have miscanthus and nothing has been added, then this has had a negative effect. But on top of that, this is even more you have to subtract. So it means that in all other cases, when it's cicale, this here will be removed, so there's a bigger nitrous oxide production in cicale. But it also means that if you have added nitrogen to miscanthus, then suddenly you will have a bigger effect. So you have to sit and look at it for quite a while to get hold of it, but I'll just read this. So how do we get this table? It's a little complicated to do. So if you look at, in fact, be easier to do it in Excel. But here I've been stubborn trying to do it in Mathematica. So what you need to use is grid, and you have to look in help how to set this up, and you have to play a lot with these curly brackets, how it will end looking. But you can see here I'm setting a space, that's this one. Then I say span from left, that means it's merging all these and add this. And then the next column, you can see here, or the next row, which is this one, will be AC. Then I put these values, which is them, I put a space. And then I make a prepend on all this, so I add, that's because I put this on top of A, which is a treatment combination order. So that's these numbers, I put them on top of this. And by doing that, I will end up having the raw and the scale data. And then down here in this one, I create the input by using two table forms. So I can say this is crop, this here, and this here is glucoses and nitrogen. And there I can see the ratio. So if I look at these raw data, you can see that the production increase when you add acetylene, but of course it will do, because now you collect all of it, nothing is getting away by getting into pure nitrogen. But you can also see that it seems like miscanthus is always producing more compared to cicale. So if you look at the scaled, you can see the effect of adding both glucoses and nitrogen is that you will have a production rate 2 times higher here, and with cicale the effect is even higher. And this is probably because the soil of cicale doesn't have so much humus, because it's an annual crop. The other is a perennial, so that's more humus in the soil, and it's more, the bacteria are more used to operate there. So this is really giving an effect. And that's the same pattern here. If you look at the ratio, you can see miscanthus, this is a ratio between having no acetylene and having acetylene. So it's saying that 80% is being produced as nitrous oxide here under normal condition, whereas cicale even more is escaping as nitrogen, which is not bad for the atmosphere. if you look into this master thesis that you saw in the beginning, and we go to page 43, this one, which has also been published, you can look at that reference. If you look at these data here, you can see it's not, I think there is room for seeing both. It's not exactly the same, but that's because here I was using SAS at that time, and I was not capable of looking so much at the data and do the filtering as I can do in Mathematica. You can do it in SAS, but I didn't have the capability at that time. But you can see the overall pattern is the same, that if you add both nitrogen and carbon dioxide, you will have a higher effect in Veterinary, which is in fact Giganteus. Where did we have it here? Here. So it's almost 3 times, so that's also what we see here. It's lower for Giganteus, not all the same here. So it can be because I haven't removed the data from 200 and up, and that will damp some of them. So that can be the case. It's also saying that the ratio is higher for Giganteus compared to Veterinary, and that's also what you see up here. So it seems like we are on the same track. And if you read this, apparently there are 2 tables at the moment, and what is happening here? Remove that one. So what is stated here is in fact the same. That the response was higher so that was expected, and it's saying here that the identification was approximately 30% higher for Giganteus. So that's the same for us, perhaps not the number, but the trend at least. So what we found out here is that it seems valid to use Mathematica for this analysis, and it's really nice. And you can go through it, and I hope I can get so you can download this sheet here and you can start to play with it. I tried to put the Excel sheet so you can play with it yourself, and if you look at this you can really get some nice experience too. So it was a long talk. Hopefully some of you can benefit from it, because I missed something like this to help me start up using Mathematica.